First, I would like to thank the organizers. So thank you for inviting me. Today I will present you two works. So a work on tridendriform algebras without saying the word tridendriform, with Jovana, Obradovic and Pierre-Louis Curien, which was published in 2025, and a work in progress with also Jovana and Pierre-Louis on orders. So I will first start with main examples in the literature. Most of you know them, but I will still recall them. Then I will present the description of nestohedra we are using, which is called hypergraph polytopes. And on the third part of my talk, I will present algebraic structure on faces of nestohedra, so an order and shuffle product. So first, shuffle of packed words and planar trees. So most of you know permutohedra. Permutohedra, it's a polytope. Its vertices are indexed by permutations, and its edges are indexed by surjections or packed words. And as we saw this morning in Nathan reading talk, so permutations are represented as a word, pi1 to pi m. And there is a poset associated to permutohedra, which is called the weak order. So the principle of the weak order is that we rise in the weak order by just switching adjacent letters in the permutation. So for instance, start with 1, 2, 3, 4. You can exchange 1 and 2, or 2 and 3, or 3 and 4. And what you get is these three elements. Then once again, you can also invert, for instance, in 2, 1, 3, 4, you can't inverse 2 and 1 because 2 is bigger than 1, so you can't apply the covering relations, but you can exchange 1 and 3, or 3 and 4, and so on and so forth. You get a poset. The minimal element is here, the maximal element is here, and the assay diagram of this poset is the one skeleton of the permutohedron. Don't hesitate to stop me or ask questions whether there is something unclear with my presentation. Okay. So now there is another one on structure on permutation, which is a Hopf algebra structure. Let us first define the product on permutations. So we start with an alphabet, and we look at when we have an alphabet, we can define words on the alphabet, and on words we can define this product, which is the shuffle product, which is defined by choosing first the letter of the word on the left or the first letter of the word on the right. And so there are two choices. Okay. So using this shuffle product on words, we can Malvenuto-Reutenauer defined a shuffle product for permutations, which is by the first. So we take two permutations. Let's take pi, a permutation of a set with p elements, and sigma, a permutation of a set with q elements. Then what we want to get is a permutation of p plus q. So we will shift sigma by p, the length of pi, and we will shuffle. So here I call that the horizontal shuffle. It's a shuffle on positions of the letters of the words. So here, for instance, considering 1, 2, 3, 2, 1, you first shift to 1. So you get 1, 2, 3, 5, 4, and then you shuffle the position of the red letters with the orange letters, and you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different elements in the shuffle product of these two permutations. So why horizontal shuffle? Because we can represent permutations as tables. And horizontal shuffle is just a shuffle of columns of these tables. So I announced to you Hopf algebras. So Malvenuto-Reutenauer defined Hopf algebras on permutations so what is an Hopf algebra? An Hopf algebra is an algebra with a product and a coalgebra with a coproduct. And to have an Hopf algebra, the coproduct must be an algebra morphism. So here we will define this coproduct, and it satisfies that this is an algebra morphism. So if we take the coproduct of two products, then it's equal to the products of the first parts of the two coproducts and the second parts of the two coproducts. Okay. So how do we define this coproduct? To define this coproduct, we have to introduce the notion of standardization. So there is a mathematical definition of the standardization. I like to use the definition in terms of tables. So when you consider words with a table, here 7 gives a dot on the 7th row, 6 on the 6th row, and so on and so forth. So the standardization of this word, which is not a permutation, is obtained just by deleting the rows of the tables which are not used. So using this notion of standardization, the coproduct of Malvenuto-Reutenauer Hopf algebra is obtained by just considering the p first letters of the permutation, standardizing what we obtain, and this gives the left terms, and the right terms is the other letters. So for instance, on 1, 3, 2, we can choose no letters, we get the empty word. Or we can choose just the first letter, 1, and 3, 2 gets standardized to 2, 1. Or we can choose 1, 3, which is standardized to 1, 2, and 2 give 1. Or we can choose the 3 letters of 1, 3, 2, and we get this term in the coproduct. So we get a Hopf algebra on the elements which are the vertices of the permutohedron. And Loday and Ronco proved in 2002 that there is a link between the order on elements of the permutohedron and this shuffle product on permutations. So there are two products. So they satisfy duplicial relations, but if you don't know duplicial, they satisfy some. There are some products. So this first duplicial terms is obtained by just concatenating sigma with shift of tau, and the second one is obtained by concatenating first the shift of tau with sigma. So with 2, 1, 1, 2, we will get the interval between 2, 1, 3, 4, which is the shift of 1, 2, and 3, 4, 2, 1. So it's a bit small. I hope you can still see something. So here is 3, 4, 2, 1. Here is 2, 1, 3, 4. And the interval is this diamond shape with these little edges. So we get 6 elements. For this relation. Okay. So I talked to you about horizontal shuffle. There is another kind of shuffle on permutation, which is a vertical shuffle. Instead of shuffling the position of letters in the permutation, you can shuffle the values of letters in the permutation. So instead of shuffling columns, you shuffle rows, and you get these tables. So mathematically, we take the sum over all permutation ST, such that the first part can be standardized to sigma, the second part can be standardized to tau, and we get the vertical shuffle. So the vertical shuffle is the shuffle that we must use to have a tridendriform algebra, and it's also the shuffle which is the shuffle considered on packed words and surjections. After the results of Loday and Ronco, Chapoteau introduced an Hopf algebra structure on faces of the permutohedron, so in terms of permutohedron, and Iverno-Villers-Thibon introduced them in terms of symmetric functions, calling it WQ sim, and Bergeron and Zabrocki introduced it in terms of NQ sim star. So when I say packed words, you can hear surjections, that's quite the same. So a packed word is a word such that the set of letters used is an interval 1k. So that there are no empty row when represented it like a table. So the shuffle product on packed words is just the same as for permutations. So we sum over all the way to have a backward, cut it into pieces, such that the first pieces can be standardized to U, and the second pieces can be standardized to V. Once again, the standardization, which here is called packed for, because we get a packed word, is obtained by just deleting the empty row. So we have a shuffle on the faces of the permutohedron. In fact, so we have more than a shuffle product. We have a tridendriform products. So I will explain a bit what are tridendriforms later on. And what about the coproducts? The coproducts are obtained by just looking at the subword induced by the k first letters and the subword induced by the other letters. So for instance, here, 1, 1, 3, 2, you can consider no letters. You have this gives the first term. Or you can consider 1, 1, and you get 1, 1, and you have to standardize 3, 3, 2, which standardize to 2, 2, 2, 2, 2, 1, sorry. Or you can choose 1 and 2. If you choose 1 and 2, you get 1, 1, 2 here. And 3, 3 is standardized to 1, 1, and so on and so forth. So once again, it is a Hopf algebra. This coproduct is an algebra morphism. And once again, there is a relation between shuffle product of packed words and sum of elements in an interval of this order. So which order? The convenient order was introduced by Palacios and Ronco in 2006. So here it is, I just passed the definition of Palacios and Ronco in terms of surjections. I've tried to translate it in terms of packed word here. So it means that you have some I in your word, and there are all the letter I, and then just after there are all the letter I plus 1. There are no shuffles between I and I plus 1. So you have all the I, and then all the I plus 1. And if you have this configuration, then this packed words is smaller than the packed words obtained by shifting the I plus 1 to I. On the other side, if you have all the I plus 1 and then all the I, it is bigger than the packed word obtained by shifting this I plus 1 to I. So this defines an order on faces of the permutohedron, and the results of Palacios and Ronco is that the shuffle product of packed words is exactly expressed in terms of sum of elements in the interval. Okay. So there are two polytopes in the title of this conference, permutohedra and associahedra. So here is associahedra now. The faces of associahedra are labeled by planar trees. The vertices are planar binary trees. So the faces are planar trees. once again, as you know, there is a poset structure on the one skeleton of the associahedron, which is the Tamari order. So I didn't recall this, the Tamari order. I just drawn examples on various combinatorial objects. So I forgot to put 3-1 to avoiding permutations, but here are other examples of Catalan objects with endowed with Tamari order. In fact, what's important to me is not really the definition of Tamari order, is the link between Tamari order and once again some Hopf algebras. So Loday and Ronco introduced Hopf algebra on planar binary trees in 1998. So once again, instead of shuffling words, we shuffle trees, planar trees. So the shuffle of this tree and this tree is obtained by summing over all the way to shuffle. Summing over all the way to shuffle elements on this right branch with elements on this left branch. And here you get 6 terms. And Loday and Ronco proved in 2002 that the shuffle product of S and T can be expressed as a sum of elements in an interval whose bounds are given by, once again, duplicable operation. What are the duplicable operations? They are here. So one of the three, so I always mix the max and the min, but one bound of this interval is this tree. So you just graft T S on the top of the right branch of T, and the other one is this one. The other bounds is this one by grafting T just at the end of the left branch of S. Okay. So Loday-Ronco and Chapoton extended these shuffles to planar trees in the way you can imagine. So just once again, you shuffle the tree of the left branch with the tree of the right branch, but here you can have at the same position vertices from the left and vertices from the right branch, and you get a shuffle of planar trees. So the obtained product is associative. It is a free associative algebra, but generated by finitely many generators. And this was the motivation for the introduction of tridendriform algebra by Loday and Ronco. So what is a tridendriform algebra? It's splitting this associative product according to the root of the considered tree. So these trees have roots coming from the left, so it will be a left product. These trees have roots, these 3 trees have roots in both trees, so it will be the dot product, and the other 5 trees have roots on the right, so it will be a right product. So this, the tridendriform algebra of planar trees is a free tridendriform algebra on one element. Okay. So once again, Palacios and Ronco introduced in 2002 the following order on planar trees. So here, it's a covering relation. You consider the order generated by this covering relation, and you get an order. Palacios and Ronco prove that the shuffle product of planar trees is the sum of elements in an interval of this order. So this was quite a big introduction to what I'd like to present in this talk. The goal of this talk is to explain to what extent this construction can be generalized to other polytopes, and more precisely to nestohedra. Do you have questions on the examples? Okay. So my second part is on hypergraph polytopes and nestohedra. So here are usual polytopes, and we started with this simple question. You have simplices, hypercubes, associahedra, and permutohedra. Could we define a Schoeffer product and an order on their faces with one linked with the other one? So for permutohedra and associahedra, it was known. For hypercubes, there were Hopf algebra, but not linked with order on faces, and so also for simplices. Okay. So the description of nestohedra that I use is not the one of Postnikov, it's rather the one of Dojan and Petrich in terms of hypergraph polytopes that you would call hypergraph associahedra. So considered a hypergraph, what is a hypergraph? A hypergraph is just like a graph, but edges are not only between two vertices, it's between 3, 4, between a set of vertices of cardinality at least 2. So here, for instance, you have a hypergraph, and there is an edge C of cardinality 4 with 1, 2, 5, 6 in the edge C, and so on and so forth. So in this talk, all the hypergraphs I considered are considered connected also. Okay, so how do we go from hypergraph to nestohedra? How do Dojan and Petrich go from a hypergraph to nestohedra? In fact, the edges in the hypergraph prescribe some truncations of faces of the simplex, and it gives a nestohedra. So for instance, consider this flag hypergraph here, 1, 2, 3. There is an edge between 1 and 2. So this hypergraph is obtained from this simplex by cutting the intersection of face 1 here and face 2 here. So we get this, which is for me is a square. Combinatorially, it's a square. So let's move on. When we add one vertex to this flag hypertrees, what do we get? We get the polytope, which is obtained by truncating the intersection of face 1, 2, and 3. So 1 and 2 are here, 3 is behind. The intersection of 1, 2, and 3 is just the top. It's just this element. So we cut the top of the simplex. And then there is also an edge between 1 and 2. So we just cut the intersection of face 1 with face 2 along the edge. So we cut that thing. And what we get is a cube. So in using the description of Dojan and Petrich, I will talk about constructs, but for most of you it's called tubings. So the point of view of constructs and tubings are just quite the same, except that I like to see trees from the side, and here the tubings are just what you get by looking, by looking at the tree from above. All the tubes in the tubings are the upper radial in the tree. Oui?
If, for example, you have two edges like 1, 2, 3, and 1, 2, 4.
Yeah.
Do you want these two cuttings to not touch one another, or are they allowed to make?
Yeah. So if you have 1, 2, 3, and 1, 2, 4, then it means that you cut the top 1, 2, 3, and you cut the 1, 2, 4. Yeah. You cut two vertices.
You don't kind of touch each other, right?
No, you cut, yeah.
Okay.
Yeah. No, if you have 1, 2, 3, and 1, 2, 4, you will only cut the two.
You want to put like big, tiny amount.
Yeah. Yes?
So I thought for Postnikov he doesn't do this for any hypergraph, but for these building sets.
Yeah.
Which is a subset, I think.
Yes.
But so are nestohedra a subset of hypergraph polytopes, or do they all arise?
They're equivalent. Dojan and Petrich proved that this description of polytopes in terms of hypergraph polytopes gives exactly all the nestohedra. So it's not obvious, but they are equivalent. So instead of speaking here about tubings, I will talk about constructs. So what are constructs? The constructs are just trees whose vertices are indexed by partitions of the set of vertices of the hypergraph. And so the construct can be obtained by just considering a tree with one node labeled by just the whole set of vertices, or it can be defined inductively by choosing a subset of vertices. This will be the root of our construct, and then for each connected component of the hypergraph obtained by removing this set, we choose a construct. So here, for instance, still with the example of my square, if I choose 1, then the both edges 1, 2 and 1, 2, 3 will pop like bubbles. It will pop, so it will disappear. And the obtained hypergraph will be completely disconnected. There will be two connected components, the connected component 2 and the connected component 3. So there will be one subtree for each of these connected components. Okay? So that's also the same if you remove 2. But if you remove 3, then only the edge 1, 2, 3 will pop. And what remains is a hypergraph with one edge, 1, 2. And then you can choose to first delete 1, or first delete 2, or delete both. So first you delete 1, and then it remains 2, or you choose 2, and then it remains 1, or you choose both, and you have this thing. Okay. So here, when at each step you choose the smallest possible set, what you get is the vertices of your polytopes. Here is 4 edges of the square, and here, if you choose everybody, it gives the interior of the polytope. Okay. So the second example, I tried to draw it. Perhaps it's a bit small, but okay. So it won't work here. Okay, so here is the face 1, and the construct of the vertex, which is opposite to this face, will start with 1. So there is only one construct starting with 1, which is this construct. For 2, that's the same. So for 3, when you choose 3 in the hypergraph here, then there are 2 connected components, 4 and 1, 2. So this gives these elements. It's not true. I correct it. Yeah.
So when you delete the vertex, you remove all hyperedges that contain it.
Yeah.
They're not projected.
No, you pop it. And okay, and here at these vertices you get 4 elements. And how do you label the edge between 2 constructs? This edge is obtained by just, in fact, these elements are just obtained by some kind of flip. And here you choose first 1, here you choose first 3, so here you choose first 1, 3, and so on, so forth. Okay, and here I didn't complete my drawings, but here this face is obtained by choosing both 4, 1, and 3. So you take 1, 3, 4, and 2. So this face is 1, 3, 4, 2. Is it clear? Okay. So that is how we see our polytopes. And why do we like this description? Because combinatorially, it will be just dealing with tree-shaped structures and defining operations on tree-shaped structures. So recalling that, so I presented the simplices, hypercubes, associahedron, and permutohedron. The associated hypergraphs are the following hypergraphs. I didn't say, but in fact, there is not a unique hypergraph associated to a polytope. So here, for instance, for the associahedron, we can consider this hypergraph. I've drawn the minimal hypergraph, but we could also consider the hypergraph with an edge 1, 2, 3, or with an edge 2, 3, 4, and it will be a different hypergraph, but the same polytope. Because if you, I didn't say that, but if you remove the intersection of 1 and 2 and the intersection of 2 and 3, then you have to remove also the element of the top, so the intersection of 1, 2, 3. Is it clear? Okay. So these are the photos of the polytopes, the associated hypergraph. They are associated combinatorial objects. So as you know, what labels the faces of the permutohedron is packed words. For associahedron, it's planar trees. For hypercubes, is what we call left comb trees. So it's trees, but with only children on the left. It's like combed to the left. And for simplices, we can also, so, sorry. Here is a description in term, we can describe it in terms of left comb trees, but it can also be seen as sequences of 1, minus 1, and 0, and sequences of 1, minus 1, and 0. It's equivalent. And for simplices, it's multi-pointed sets. Okay, so finally. What algebraic structures are we defining on faces of nestohedra? So first, our heuristics on shuffled product was that we wanted to define a shuffled product of two constructs as a linear combination of constructs having root A or root B or both roots. And the natural thing to do is just summing all these things, but it doesn't work for hypercubes. So for hypercubes, so we want to have tridendriform algebra. We want this shuffled product to be associative, and to have an associative product here, we can't just sum up constructs like we lack. In fact, what works is taking the sum of constructs having root A, construct having root B, and removing construct having root A union B. So this equality is not satisfied if here is a plus, and it will be satisfied if it is a minus. So let's define a bit things. So when you define functions from some sets to another set. So here is what we are doing. We are defining functions from construct of some hypergraphs to construct of a big hypergraph. So we considered a collection of hypergraphs, and we are going to a hypergraph. We have two kinds of restrictions on this family. So these restrictions are on the connected component. So here, what we want for strict families. So imagine once you have removed your root, the sets of the root, then you have connected component. And what we want in the strict case is that if here this bubble is connected, then it is also connected in the big hypergraph. So we want that if things are connected in the small graph while removing the subset XA, then it is still connected in the big hypergraph. That's a necessary condition to have right equations. So if we have this condition, then so when are these conditions satisfied? These conditions are satisfied. The strict conditions are satisfied for associahedra, permutohedra, and restrictohedra. And we wanted also to deal with hypercubes. So to deal with hypercubes, we have introduced the notion of quasi-strict. And for quasi-strict, we also, so we want the connected component of the small graph to be either included or in the connected component of the big graph, or to be totally disconnected. So just think about what happens in the case of hypercubes. For hypercubes, so we have these hypergraphs, and imagine that you consider something like a map from construct of one, two, three. Do you see, or do you want me to put on, to switch on the light? Okay, so if you look at what happens for hypercubes, here this is connected. So imagine that x, for instance, is 2. Okay. So if you remove 2 here, it's totally disconnected. If you remove 2 here, it's totally disconnected. But here, as there is no 2, it's still connected. So to deal with this case, we allow this second case that here, either this graph 4, 5 is connected here or totally disconnected. This is what happens for hypercubes. Okay. So we have introduced shuffle products for these hypergraphs. So in fact, we have introduced tridendriform products, but these give shuffle products for these graphs. And when do we have an associative product? So we still have a condition on hypergraph of the family. We want these drawings to be the same as this drawing. So we want some kind of associative condition. Just remember associative condition. And what we get is that the shuffle product obtained is associative if the family is strict or if it's quasi-strict, and we have this -1 coefficient in front of what we get when we choose root from both sides. Okay? In fact, I flashed really quickly this slide. It's here, the Q is here. So this Q can be whatever you want in the strict case. In the quasi-strict case, it must be Q equal to -1. So we got our associative products, and we have introduced an order on faces of the nestohedra that we call the generalized flip order. So it was introduced by Curien and Forcey in their paper, and we use this order. It extends the order on vertices of Barnard and Macronville. And using this order, what we get is a link between our shuffle product in the strict or quasi-strict case and sum of elements in an interval of the generalized flip order. So it was proven by Ronco in 2012 for graph associahedra, and here we obtain it. So we obtain new case like nestohedra and hypercubes. I think that our order is a bit different. On examples, it seems a bit different, but the idea is quite the same. So what is this order? So we say that S is covered by T if we have so either something like I will. So let's say that M. I don't know how to write it. Perhaps just. So let's consider that we have the minimum of U, which is bigger than the maximum of V. So we write like U is bigger than V. And if U is bigger than V, then you have the relation UV is covered by, with the things around, is covered by this thing, and UV is covered by VU. So perhaps I can just draw the example of the hypercubes. So on associahedra and permutohedra, it coincides with the generalized Tamari order defined by Ronco. On hypercubes, for instance, we get so that this tree is smaller than this tree. I won't have enough places. Okay. So above 2, 1, 3 is 1, 2, 3. Above this one is 1, 2, 3. And above both is 1, 2, 3. So it's a bit ugly, but so here is the maximum element, and here is the minimum element in the hypercubes. Okay. Finally, I've talked to you about Hopf algebras. So what about coproducts? So in fact, coproducts is not so easy dealing with. So for instance, here for those you know, it's a formula inspired by Grossman-Larsen Hopf algebras. So on trees, given by you cut some edges on the trees, and the rooted parts go on the left, and what is above is a forest. You do the shuffle product, you put it on the right. So it is the coproduct that you get for permutohedra and associahedra, but on hypercubes that doesn't work. So that's still a work in progress. Thank you for your attention.
We have had some questions already, but maybe there are more.
So the generalized flip order for when H is a path, like a graph, this is the Tamari order? Or
Yeah.
Okay, so it's specialized to the known one.
Yes.
And
it gives, sorry for interrupting, it also gives a weak order for the permutohedron.
Yes, yes, so okay, so and there are other there are known algebras on generalized permutohedra. There are monoids on generalized permutohedra that specialize to nestohedra already, no? I mean, there are constructions.
It's possible.
Okay. Okay. So how do they compare? I mean, what's...
I don't know. I
Okay.
should see the definition.
Okay. Thanks.
I wanted to ask you if the fact that these structures have polytopes underlying them helps you understand, like, are there algebraic consequences to having a polytope, or maybe like the fact that it's a topological sphere, does that have algebraic consequences? Or?
No, in fact, to be honest, we really deal with just construct like tree-like structures on which we can define algebraic structure rather than using the polytope structure. But it's a really interesting question. I'm coming more from algebras and polytopes, so.
Thank you, Bérénice. So on any generalized permutohedra, there is a natural order on the vertices, which is you just order in the usual direction the vertices of a polytope. There is also a natural order on the faces, which is you say that a face covers another one if, let's say, F and G. If F is a facet of G and they have the same max or the same mean. So, it's not exactly what you drew there, so I wanted to ask whether you tried this natural order. Whether this order that I just defined, which is a very natural order, it's actually the Ronco Palacios order on the associahedron and on the permutohedrons. This is the orders that I defined is the same in their case. It's not the one you used here, apparently, because this is not on the square. It's not exactly the same. So did you try this one I defined on nestohedra, or did it behave poorly, or?
So you asked me if I tried the other order known and defined on nestohedra.
Yes. So you define one which is sort of different from the one which is very natural.
So I think it depends on the point of view. This one seems natural to us. So in fact, we didn't look at all the orders. What we wanted was an order for which we get shuffled products and tridendriform products. What we wanted was not defining an order. What we wanted was this formula linking shuffled products and tridendriform products with intervals in the order. So there may be other orders which works, but we haven't looked at all the order which could work. We only looked for one which works.
Are there more questions? Okay, so maybe we should thank Bérénice again.